I've enjoyed working in this program, and I believe this is something essential to fostering more mathematicians in our ranks. But that's enough about me. Let me get to introducing our wonderful instructors here today with us and to go through some math kangaroo problems. First off, we have Evan from Nevada State. Evan was a math count champion in Nevada State and a 2022 USA JMO qualifier. He has been qualifying for Amy since 7th grade and is the co-president of his school's math club. Apart from math, he enjoys skiing, learning about aviation, following the St. Louis Blues, viola, and eating bread. Our other instructor is Arya, who has been involved in competition math since 8th grade. He has qualified for Amy and coaches his middle school's math counts team. Arya's other interests lie in listening to music and playing chess. Without further ado, let's get started.
All right. Hello, everyone.
Yeah, hello. Real quick, I just want to make sure like everyone knows this. If you tap into chat relay, like in Zoom, stuff will pop up on the screen and then we can interact with you while we're solving problems. And yeah, so before we get started, just to, get to know everyone, could everyone type like where they're from and maybe what grade they're in just to get a feel for who's here?
Yeah. I see. Tester has said from Zoom. Hello, Aaron. As you can see, your messages that you send to chat relay show up over here, so we can talk with them, and that's fun. Yeah. Ooh, Aaron's in 3rd grade. Hello, Sophia, and Nicholas, and Ritve, and Karsten.
Ritvik. I have a friend named Ritvik.
Ah,
Texas.
that's nice.
South Lake.
My sister's actually in Texas right now for a camp, which is kind of funny.
Warp? Is she at Warp?
Yeah. Yeah.
Oh, that's nice. I've heard good things about Warp. Okay.
I see. Bong says hi, and Aaron says hi again. Hello, Aaron. And most people here seem to be from the United States. Yeah. I see a lot of elementary schools. That's awesome.
Panda? Okay.
Pandas, yeah.
Oh, there are a lot of elementary school students. That's interesting. Usually the ones I teach usually have more like 7th graders and 8th graders,
Yeah. I think my favorite school years before high school were definitely in elementary school, like early elementary school, because that was when I was able to have lots of fun without having to worry too much about homework. Yeah.
The year before high school was COVID for me. It was all online, so I did not enjoy that one.
Yeah. Alrighty. Well, it looks like you guys all have got the chat down working well. So let's go to the first question. And it is a long one, or at least many answer choices. So long this way. Anyway, Jenny's looking at a weather app on her phone that shows the predicted weather and maximum temperature for the next 5 days. Which of the following graphs is the correct graph for the maximum temperature? Alrighty. Well, we see that on Friday, it's -1 degree Celsius. On Saturday, it's -2. On Sunday, it's 0 degrees. On Monday, it's 6 degrees. And on Tuesday, it's 2 degrees. My goodness, this place must be either Ontario, Edmonton, or Siberia, one of the three. Aaron and Carson are all saying B. Yeah, I agree with you guys. It is B because on Friday, it's -1. It goes down to -2 for Saturday, up to 0 for Sunday, up to 6 for Monday, and down for Tuesday. If you just compare Monday and Tuesday, you'll see that Monday is higher than Tuesday, which immediately narrows it down to either B or D. But then for option choice B, the second day is warmer than the first day, which is obviously not the case. So we have option B. Yes. Nice problem to start.
All right. Let's go to problem 2 then. There we go. Okay, this is pretty long. The halftime score of a handball match was 9-14, so the visiting team was leading by 5 goals. After their coach made a change in strategy at halftime, the home team dominated in the second half and scored twice as many goals as their opponents. The home team won the match by 1 goal. What is the final score? Okay, I'm just gonna write down the information, from one by one. So I'm gonna label this be home team and then visiting team. And the visiting team is leading or winning in the first half, which means these guys are 14-5. Wait, not 5, 9. 9. That's what we have at halftime. But in the second half, the home team scored twice as many goals as their opponent. So these guys made like 2x goals in the second half, while these guys, the visiting team, made X goals. And that means at the end of the game, this total score was 2x to 14 plus x. And then we're told that the home team, which means this team, won by 1. So 9 plus 2x equals 14 plus x plus 1. Or subtracting them equals 1. Either way, we solve for x now, and we end up getting 6.
Yeah. Let's see. Are
Oh,
we right?
what was the final?
Oh,
Okay. Well, I didn't kind of finish solving the problem because the question asks us to find what the final score of the match was. So I guess it's important to read the question. So we
yeah.
know x is 6, but that means that the final score is you plug x into this thing right there, and then we get 9 plus 12, which is 21 to 20, which is option B.
Yeah, that was fun. It is indeed option B, 21 to 20. Well done. Alrighty. So the next question, problem 8. A rectangle with a perimeter of 30 centimeters is divided into 4 parts with a vertical line and a horizontal line. One of the parts is a square, so it always drives exactly 10 miles per hour under the speed limit. And it has an area of 9 centimeters squared, as shown in the figure. Yeah, 9. What is the perimeter of rectangle ABCD? All right. Well, the first thing we can do is say that the square has area 9, so its side length is 3. We can draw 3's all around. And of course, rectangles are nice because opposite sides of rectangles are equal. So this side length here, the one in yellow, is also a 3. This side length here in yellow is also a 3. Alrighty. And in chat, Garrett says to subtract 3's for the side length. Yeah, we could do that. So why don't we set x equals this short side length, and y equals the long side length. Well, do you think that's a good idea? I don't think so, even though it's a natural idea, because we don't really know enough to find both of them. So that's kind of annoying. Yeah, so we definitely don't want to solve for x and y, the side lengths. But like Garrett said in chat, we could subtract 3 because the perimeter of ABCD is, the perimeter of the big rectangle is 30. And if we take away all these 4 3's, well, we're actually just left with the perimeter of the inner small rectangle that we want, right? Because if we x out this side, x out this side, x out this side, and x out this side, we're just left with this side, this side, this side, and that side, which actually come together to make ABCD. Yeah, and so since the perimeter of the whole rectangle is 30, we can take 30 minus 4 times 3. We're taking out all of these 3's here, which is 18. 30 minus 12 is 18. Yeah. And indeed, 18 is the answer. Although in this case, it would be 18 centimeters. I don't think you need to care about the units, just so long as they don't give you one side length in meters and the other side length in centimeters. That could easily mix you up. But luckily they were nice and everything's in centimeters. So onwards.
Awesome. Okay, let's go to the next problem. Okay, a lot of words again. Tom had 10 sparklers of the same size. He lit the first one when only a tenth of it remained. He lit the second one. Oh, well, he lit the first one. Wait, he lit one first. When only a tenth of it remained, he lit the second one. When only a tenth of that one remained, he lit a third one, and so on. The sparklers burn at the same rate along their entire length. One sparkler will burn for 2 minutes. How long did it take for all 10 sparklers to burn? Okay, that was a bit of a challenge to read, but I think I got a handle on it. So we have a sparkler, and it takes 2 minutes for the whole thing to burn. And since it burns at a uniform rate, if we have all 10 sparklers in a row, let's imagine there's 10 sparklers. When this is like down here, when it's burned 9/10 of the way, he starts lighting this one. So let's figure out how much time he waits before he lights the second sparkler. And since it burns at a uniform rate, this is just going to be 9/10 times 2 minutes, which is 9/5 of a minute. And we can kind of do this, like, keep going, right? So he burns the second one. So he waits 9/5 initially, like 9/5 initially, before he burns, and was when he burns the second one. He burns the third one when he waits another 9/5, and so on. And he burns the 10th one when he waits 9/5 for like the 9th time. So we really just have 9/5 times 9 is how much he waits before he burns the 10th sparkler. And then for the 10th sparkler to fully go, like, burn, it takes 2 minutes. So we're going to add 2 minutes to this. And, all the other sparklers before this obviously have all burned down because each one only takes 2, and this is definitely longer than 2 minutes. So in the end, we have like 81. Oh, I'm off screen a little bit. Oops. So in the end, we'd have like 81 over 5 plus 2 minutes, which ends up being 16 plus 2 and then plus 1/5. This is equal to 18 minutes, and then 1/5 of a minute, which is also 12 seconds. Is that an option? 18 minutes and 12 seconds
Yes,
is.
option B.
Yay.
Yeah. And that's right. Yeah. Yeah. I remember in our science writing class a couple of days ago, we were sort of doing this, except with capacitors. And obviously don't try this at home. But the fun thing was the capacitors, they have a voltage that you're supposed to charge them at. But if you charge them at more than that voltage, then after a certain amount of time, it starts puffing and then it goes pop. And the pop is a really cheerful sort of pop. At least I thought so. So we were doing that during our English class. Anyway, what we weren't doing in our English class and what we're doing now is math, though. 2021 has a remainder of 5 when divided by 6, 7 by 8, and by 9. Oh, 7 when it's divided by 8, and also 7 when it's divided by 9. How many positive integers less than 2021 have this property? Well, we actually can write this as, yes, like Garrett has said in chat, modular arithmetic. So 2021 has a remainder of 5 when divided by 6. So it would be 5 mod 6, where basically this mod means that if you take the remainder when you divide by 6, it'll end up being 5. So all the 5 mod 6 numbers are 5, 11, 16, 21. Oh, no, sorry. All the 5 mod 6 numbers are 5, 11, 17, 23, 29, and so on. But it's also 5 when divided by 7. So it's 5 mod 7 and 5 mod 8 and 5 mod 9. So basically, 2021 is 5 times a multiple of 6, 7, 8, and 9. Well, we want to find all the positive integers less than 2021 that are also 5 more than a multiple of 6, 7, 8, and 9. So I just saw a message in chat. Who said that? Like Alex just said in chat, we take the LCM of 6, 7, 8, and 9 to find the thing. To find the number whose multiple 5 more than that is the number we want. Yeah. And that is the least common multiple of 6, 7, 8, and 9. So LCM of 6, 7, 8, and 9. Now, I like to take LCMs by looking at, oh, where's the highest power of 2? That's 8, 2 cubed. This is 8 times, the highest power of 3 is in the 9. That's 3 squared, or 9. And then all of these are only divisible by 2 and 3, so we're left with the 7, and that is the only other prime factor here. So this is 72 times 7, or 490 plus 14. Normally I do this in my head, but it's fun to write things down, especially since now I can gesture at them. I can literally wave my hands. And this becomes 504. Alrighty, so yeah, like people are saying in chat, we want 504 times something plus 5. Or basically, this all amounts to 5 mod 504. All right, let's go to a new screen. We want the number of numbers that are 504 times something k plus 5. How many are there? Well, there's 504 plus 5, 504 times 2 plus 5, 504 times 3 plus 5, and so on. All right. Yeah, like Aaron says, the multiples of 504 we care about are 504, 1008, 1512, and 2016. Alternatively, we could note that the largest one, which is 2016 plus 5, or 2021, is 504 times 4. So maybe we should just say 504 times 1, 504 times 2, times 3, and times 4. But we know we have to stop at 4. Do we have to stop at 1? Could we go to 504 times 0 plus 5? Well, looking at the question, 504 times 0 plus 5, which would just be 5, would also have a remainder of 5 when divided by 6, 7, 8, and 9, because it's 5. So this edge case is one we definitely don't want to forget. So let's leave it in there. We didn't forget you, 0. You're very important. You're better than nothing. Yeah. So in fact, we're left with 5 integers that have this property. Yes, we don't want to forget 0. As they say, 0 is least, but if you forget it, it will be the last thing you do. So, yes. 4. Wait a second. Answer is saying 4.
I think it might have said less than 2021.
Less than 2021. You're right. Yeah, that was my first thought. Wait, are we not supposed to count 2021? Yes. So that is another edge case we need to take care of. In this problem, yeah, you can forget about 4. It's worthless. Nothing. Terrible. And we want 4 positive integers. Yeah, like Aaron says, less than excludes 2021. Yeah. And that is 4.
Definitely do not have fond memories of the number 2021.
Yeah, that was a
Unfortunate.
very bad year.
Okay, let's go to the next one, which is, oh, that's a problem I did before. I have race cars now.
Yeah, they were just so enthusiastic. They wanted us to do the sparklers question again.
Okay. I feel like I get the problem with the big paragraphs. I think that's unfair. 5 cars participated in a race, starting in the order shown. Whenever a car overtook another car, a point was awarded. The cars reached the finish line in the following order, and then it gives you the order 3, 5, 1, 4, 2. What is the smallest number of points in the total that could have been awarded? Okay, this is interesting. So I'm gonna write down like our order and the order we want to get to. So right now we're in the order of 1, 2, 3, 4, 5. And we want to, that's here, I'll write it below so you guys can see it better. 1, 2, 3, 4, 5. That's where we are right now. And we want to get to 3, 5, 1, 4, 2. So right away, I guess the thing to notice is that 1 and 2 definitely have to pass 3 in order to get to the second situation, like the final situation. Because if 1 and 2 never pass 3, 3 is never going to be on the left side. So I think we should just go algorithmically, like step by step, and that'll probably give us the minimum. Well, it definitely will, because we'll do the minimum amount of steps needed at each place. So right away, this would go to something like 1, 3, 2, 4, 5, which we have a running total somewhere. Let's say put it up here. Let's add 1 to the running total of points. And then the next step would be to put the 1 in front of the 3 again. So it'd be like 3, 1, 2, 4, 5. So we add 1 more to the running total. And notice that now we have 3 in the right place. And using the same logic, if we want 5 to be in the second last place, 1, 2, 4 all need to pass 5. And that's going to give us 3 points when each of those passes at the very least. So we're going to add 3, and using like the same process we did above, this would give us like 1, 3, 5, and then 1, 2, 4 in that order, because yeah, they would pass in the same order they're in. And finally, we need to get, and remember that this is like our target order. So we just need 4 to be behind 2, which would be 1 more pass as we swap these two, and then we'd get to that. So adding up the totals, we did a total of like 6 passes, so 6 points. And the answer is D, I think.
Yeah.
Let's see, that's right. It is right. Okay, awesome.
Yeah. I was thinking though that if this were something like a professional sport that's scored this way, well, the drivers could form a pact to start the race really slowly and just keep shuffling. So 1 goes to the front, then 2 goes to the front, then 3 goes to the front, then 4 goes to the front, then 5 goes to the front, so that they all rack up more points and set scoring records for the season. And then if any of the drivers start acting in bad faith, like they break the arrangement, well, then the other cars can just all pass them and go on and keep continuing. But I don't think that's the point of the question. So yeah, that was a fun little algorithm. Yeah. Yeah, I saw someone in chat said, or actually, I saw that Aaron in chat said that he made tokens to fiddle with to do this. That is a good way to do it, because then you can actually physically move them around and count the number of points. Alrighty. We have 8 boxes in the strip shown. Aha, this is another short paragraph, Arya. Haha. Numbers in adjacent boxes have a sum of A or A plus 1 as shown. The numbers in the first box and the 8th box are both 2021. What is the value of A? You know, I suspect as we go through this problem, there will be things that cancel towards the middle, and we might get something like 2021, 2021 here. Good things happening from there. But I think a good way to start would just be to fill in this box, and then that box, and then that box, and then that box, and so on, until we find something that will cancel. So these 2 boxes sum to A. So this box here is 2021 minus A. So here we have, I'll use red for the bottom and, no, that doesn't make sense. I'll just use arrows. 2021 minus A. And here we have, what do you guys think? These sum to A plus 1, right? Ah, Matthew Chong is very close. He says A minus 2021. That's good, because that would completely cancel out our previous term. But then since they sum to A plus 1, we'll want to add another A plus 1 on top of that. So in fact, it would be 2A minus 21 plus 1, which would be minus 2020. Yeah, so I see Karsten just said that in chat as well. Nice, nice. So then the third box here sums to A. And now I'm going to draw from the top because I'm running into space constraints here. These sum to A. Well, what can we add? First, we want to get rid of this pesky minus 2020. So let's add 2020. And then we're left with 2A. 2A to A minus A. So this is 2020 minus A. Well, that's nice, because this is 2021. 2021 minus A. This is 2020 minus A. If the pattern continues and we get similar stuff along the line, well, then eventually we'll get something like, oh, 20 something minus some A is equal to 2021, which is precisely what we want. So let's quickly continue on and see where that takes us. Alrighty, in this box here, 2020 minus A plus this box goes to A plus 1. So it is, actually, I should color code these. That would make it better. Yeah, often when I work on a problem, I find myself thinking, oh, this would be a smart way to organize my work. But then I think of that like 2 times as I do the problem. So I have a couple different organization systems on paper, which is sometimes not so helpful. But anyway, this box here sums with 2020 minus A to make A plus 1. So we would make this 2A minus 2019 because we'd have A plus 1. Yes, 2A minus 2019, indeed. Alrighty, pink, like a lemon. Alrighty, these 2 boxes sum to A. So 2A minus 2014, and this box sum to A. So of course, the box is 2014 minus A. Alrighty, and this final box, which is yellow, like a grapefruit, sums with 2014 minus A to get A plus 1. So it is 2A to get the A minus 2013 to get the 1. Yeah. I see a 6th box. Carson is saying 1, 2, 3, 4, 6. Wait, you're right. This is an occupational hazard that you should do your best to avoid. This is the 2019. I wrote it originally as the 2019, and then not thinking, well, because I was trying to think of a fruit that was the least pink, which is lemon. I wrote 2014 here because, as you can see, my writing is messy. So don't do that. Write slowly and write neatly. Yeah, so this is 2019 minus A. Thank you guys for catching that. A plus 1, and the pink, yellow sum to A plus 1. So we would want actually 2A minus 2018. So yeah, 2A minus 2018. Yeah, like Carson is saying. Alrighty, and this is really happy news because as you see, we have 2A minus 2018 and 2021. They've got a sum to A. And you know what that is? That's an equation. And that's an equation we can use to solve for A. So 2A minus 2018 and 2021, they sum to A. Alrighty. 2A minus 2018 plus 2021 equals A. This becomes 3 because 2021 minus 2018 is 3. So we have 2A plus 3 equals A, or A equals -3. All right. Wait a second. That seems off. I think we've done another silly thing. Because yeah, I'll explain why I thought it was off later. But for now, let's quickly double check for the sake of sanity. Alrighty. Yeah, that is a very unfortunate thing. Starting left from right again, you'll notice that 2021 plus 2021 minus A is notably not A. I'm not sure what was going on there. That's really weird. But either way, we can start anew on this and quickly run through them again. Yeah. And for reference, the reason I was thinking that A being negative is off is because if this was -3, then the second box would have to be negative huge. And so the third box would have to be positive less huge. And so there'd be positive, negative, lots of positive and negative huge numbers. But that definitely didn't align with what we were seeing here. I think it aligns with positive, negative, positive, negative, positive, negative, positive. Oh, it doesn't even align with that. Yeah, so we'd have a positive number here, a negative number here, a positive number here, because each pair of boxes would have to be positive and negative. Yeah. Anyway, if you keep on doing that, you would get that 2021 is negative. And that was the first hint that something was off. Because 2021 is not negative. Alrighty, so this box here, like Carson said, we can negate everything. This box in yellow is A minus 2021. That sums to A. Then the box in bright green is 2022. Because A minus 2021 plus 2022 is A plus 1. And then this block in red is A minus 2021. Because, or sorry, no. This box in red here is A minus 2022 again, which is really quite nice. Because A minus 2022 plus 2022 is A. Yeah. Then the next box in pink, well, A minus 2022 plus next box is A plus 1. So the next box is 2023, because adding these two together gives A plus 1. Alrighty. Now, I think I'm going to have to reuse a color. I don't have a readily available palette on hand. So this box, gray plus pink is A. So gray is A minus 2022. Or sorry, A minus 2023. Blech. Yes. And so which box do we have now? We have the orange box. Actually, I did have enough colors. It's nice. The orange box is 2024, as you can see. Yeah. So because 2024 plus A minus 2023 is A plus 1. And actually, this gives us a really direct calculation for A, which is 2024 plus 2021, which is, wait a sec, 4,045. That's also kind of funny because I don't think 4,045 was an answer choice. And also, 4,045 is really big. All right, let's go through this question really slowly and see what I've done wrong. Alrighty. 2021 plus A minus 2021 is A, right? Yeah. A minus 2021 plus 2022 is A plus 1. Matthew says this is like using the power rule of integration on 1 minus x. Not sure it's that similar, but if you mean that this is taking longer than it should, perhaps you are right. Yellow and green, A minus 2021 plus 2022. Yeah, that's A plus 1. Yellow and red, A minus 2022 plus 2022. That's A. Red and pink, A minus 2022 plus 2023 is A plus 1. That's right. Pink and gray do make A. Gray and orange do indeed make A plus 1. All right. Karsten is saying 2022 is the third one. Yeah, I agree. Maybe we misread the problem. Here is the problem. The numbers in adjacent boxes have sums. A or A plus 1 is shown. The number in the first box and the 8th box are both 2021. Okay. Do any of you guys see what could be, what could be going awry? This is weird. Hey, Arya, do you see either? I feel like I'm going to end up.
I'm lost. I really think your
Oh.
second one is right. I'm thinking. I'm trying to find.
Yeah, this is quite bizarre because this should be a normal. I just fill in the blanks nicely and get an answer problem. All right, so yellow, A minus 2021 plus 2021 is A. A minus 2021 plus 2022 is A plus 1. 2022 plus A minus 2022 is A. A minus 2022 plus 2023 is A plus 1. 2023 plus A minus 2023 is A. And A minus 2023 plus 2024 is A plus 1. And 2024 plus 2021 is 4045.
I'm inclined. Okay, yeah, I think
Yeah.
I think this is right.
Yeah, I think this was a slight typo on the slides. So 4045 is the
Yeah.
answer. And actually going through this in my head, we could approximate it as 2000 and 4000, right? So all of these would end up being around 2000 and all of the sums would end up being around 4000, which is definitely right. So
I think we can
think-
actually. Oh, I
Mhm.
think Math Kangaroo has a website, right?
yeah, but that's okay. I think for now, since
Yeah.
4045 definitely works for this problem, and they haven't given us
Yeah.
any other constraints, I think this may be a type. Yeah. So let's move on for now, and I'll update you guys if it turns out we were wrong. Yeah. Ooh, the next one.
Okay.
All right, you'll be happy. It's a short problem statement.
Yeah. As soon as I saw it, that's the first thing that went through my head. Okay. Let n be the smallest positive integer such that the sum of with the sum of whose digits 2021. Okay. N small number, well, smallest number that has a digit sum of 2021. What is the sum of the digits of n plus 2021? Okay. This is definitely not a small number. But I have to find the smallest. And the way to do the smallest is like, I guess the more digits you have, the bigger the number is automatically because it's a bigger magnitude. So we're gonna try to use up as many nines as we can to like lessen the number of digits. And actually, Evan did the hard work for us already because in a previous problem, we found that 2021 is equal to 2016 plus 5. And 2016 is divisible by 9, which means I don't have to, like, I can just divide 2016 by 9. And I get 18, 2, 1, 2, 18, 3, 6, 4. Okay. So I get that 2016 is equal to, is equal to 2024 times 9 plus 5, which means if I want the smallest number, obviously my first digit, well, I don't want my first digit to be a 9. I would rather have it be a 5, right? Wait, yeah, that's right. Yeah. So it'd be like 5 and then a bunch of 9s and 224 of them to be precise. And the question is asking us to find the digits of n plus 2021. So I'm going to have to add 2021 to this. So let's pretend there we have some more 9s. So if I do 2021 plus this thing, I'd end up getting 0, 1, 11, 12, 2, 1, 0, 1, 2, 1. And then notice, okay, this is nice. Now I just have 0, and then these are a bunch of 9s. So when I carry the 1, it becomes a 0. And that keeps on happening, and I keep getting 0 until I carry the final one, in which I get 0, 1, and then 5 plus 1 is 6. So I have a 6, a 2, and a 2, and the rest are zeros, which means the sum of the digits is 10. Okay, and that's option A. So
Yeah, that reasoning seems right. And it's 10. Alrighty, guys. So I did a little more thinking, and I'm pretty sure this is a slide typo because let's suppose that, where's a good one with just the question? Yeah, let's suppose that A was like around 10 or so. Well, to make 8 this sum to 10, this would have to be a negative number, right? A pretty sizable negative number. And then to make it sum to a positive number here, all of the pairwise sums are positive. So not pairwise, all of the consecutive sums are positive. So this number would have to be negative. This number would have to be positive. So this number would have to be negative. Because remember, this would be a big positive number, like 2000 something. And to sum to 10 or something, it would have to be a big negative number, big positive number, big negative number, big positive number, big negative number. Notably, 2021 is positive. So yeah, 4045 is definitely the answer here. Yeah, sorry about that. That was clever of you, Arya. I like it. It always feels like such a joyous occasion when you use your previous. It's like, I
yeah.
the code. Garu, you're exactly right. 4K something. And the reason of that is a good approximation for what's going on in the problem is 2000, 2000, and 4000 all along. And everything is 2000. And that's basically right. So adding another 21 here, you'll just have to do a little algebra, and then you'll get the answer 4045. Alrighty. Last, the problem 26. Each of the numbers a and b is the square of an integer. So maybe a equals. Okay, guys, give me a variable name, and I'll use them. The first two, I'll use them for the numbers that square to make a, and the numbers that square to make b. All right. The difference A minus B, the difference of two squares, mind you, is the prime number. Which of the following could be B? All righty. Mu. Oh my goodness, Matthew, that's a terrific adjective, a terrific variable. Let us say A equals mu squared. So mu is just a fancy Greek U. And then, alrighty, B equals K squared. Well, it'll be nice and boring with a K, the normal integer. Alrighty. Well then, A minus B is mu. Oh, okay, Matthew says rho. Alrighty, we'll go with rho. Why not? So you can think of it as a P. Alrighty. Nu. I don't want to use nu because saying nu and mu will get rather confusing quickly. But I do like nu as well. It's an awesome Greek letter, one of the top 26 Greek letters. Alrighty. A minus B is prime. So mu squared minus rho squared is prime. So mu plus rho times mu minus rho is prime. Now, this means that one of mu plus rho and one of mu minus rho has to be 1. Because you can't have two non-1 numbers multiplying to prime number. Like, right, if this was 5 and this was 3, they multiply to 15, which has more than one prime factor. So we can't have that. Now, mu and p, mu and rho are both can both be approximated as positive because it doesn't really matter whatever happens. So they're both positive. So mu plus rho is positive and bigger than 1. So we need mu minus rho equals 1, exactly like Carson said. Alrighty. So mu minus rho equals 1. All right. In that case, mu plus rho equals mu plus 1. Mu plus 1, which is 2 mu plus 1. So recapping, we found that b equals 2 mu plus 1 squared and a equals mu squared. And then we noted that a squared minus b squared is a prime. So that meant a plus b, oh, sorry, that meant 2 mu plus 1 plus mu, or sorry. Yeah. Typo here. B is mu plus 1 squared, right? So this meant that 2 mu plus 1 times mu plus 1 minus mu is prime. This becomes 1, right? So 2 mu plus 1 is prime. That's kind of nice. So now we know that whatever b is, the square root of b times 2 plus 1 has to be prime. So we can use informed guesswork by them telling us that b is either 10, 12, 16, 30, or something big. We'll ignore this until later. 10, 12, 16, 30. B equals 10, 12, 16, or 30. Alrighty, guys. Help me out here. 10. If b is, if the square root of b is 10, does it work? If the square root of b is 12, does it work? If the square root of b is 16, does it work? If the square root of b is 30, does it work? All right. So I see Carson putting some stuff into chat. That's good. All right. Yeah, so this is close because if b is 10 squared, then you know that mu would be 9, and then 2 times 9 plus 1 is 19. So actually that works. But let's start working from this end, just for a little bit of fun. Suppose b was 30 squared, right? Suppose b equals 30 squared. Well, from here we'd say, oh, mu is 29 because mu plus 1 is 30. So mu is 29. And then the number we'd want to be prime is 2 times 29 plus 1, which is 2. So prime equals 2 times 29 plus 1, which is 59. Oh, Karsten, after a few minutes, the stars reset. I think it's either 10 minutes or half an hour. So that way you really want to, yeah, that way you have to keep posting good messages like you are doing to get stars. In fact, I should star those messages because they were good. Alrighty. Well, yeah, 10 is indeed the correct answer because that is the one for which our expression works nicely. So suppose b is 10 squared. In fact, now let's work it out completely, just for fun. B is 10 squared. B is 10 squared. B is 100. Alrighty. Then A is 9 squared, which is 81. So B minus A is 20, or sorry, 19, which is a prime. So 100 is the correct answer. Oh, wait, actually, wait, guys. A minus B is the one that's supposed to be prime. So we've got to do a little bit of tweaking, actually. And since A minus B is the one that's prime, A is mu plus 1, and B is mu. So if we just switch everything, then in fact, 30 is the right one because it was 30 times 2 minus 1 that was prime. Whereas, wait, no, sorry. It would be 30 times 2 plus 1 that we wanted to be prime. And so 30 would be our answer. Yeah, because A's got to be bigger than B. So swap A and B here and everything's good. And we do indeed get 30. Yeah. Or 30 squared, which is 900. Yeah. All right. So just to recap this problem, we found that A is something squared, B is something squared. The something that's squared to A is one more than the something that's squared to B. Yeah. And then the difference between A and B is mu, in this case, times 2 minus 1. And the only answer for which that works is option D, where B is 900. Yeah. Yeah, as Karsten says, still the same. All right. Yeah. Well, that was actually the last question. So, if you guys
Wait,
have got
there's
any,
one more.
there is.
Yeah.
Oh, take it away. Yeah, I did not see that one. You're right.
Okay. A lot of words yet again. That's okay. All right. Okay. Christina has 8 coins whose weights in grams are different positive integers. When Christina puts any 2 coins on one side of the balance and any 2 on the other side of the balance, the side containing the heaviest of the 4 coins is always the heavier side. What is the smallest possible weight of the heaviest coin? Okay, that was a lot to take in. 8 coins, they're different. So I'm gonna label them. I guess whenever there's like different things, and they're similar, I go usually just x1, x2, all the way to x8. And in this case, since they're different, and we're talking about weight specifically, we can sort of like let x1 be less than x2 be less than x3, and and since like particularly want something to do with the heaviest coin and like the weight of the coin matters, x8 would be the heaviest coin. Makes the most sense in my head. So yeah. And the problem statement basically says out of any 4 coins, whatever side the heaviest of those 4 coins on will be the heaviest. And this is kind of nice when we're in ascending order like this, because as long as it stays true for every 4 like consecutive terms, if you ever pick like a higher term, it'll also work. So yeah. And like just to put it in words, I guess we can take the first 4, and it's basically saying that x1 plus x4 is greater than x2 plus x3. And then taking like the next 4 terms, it says like x2 plus x5 is greater than x3 plus x4. That's kind of like the condition we want for every consecutive 4 term. And I don't, let's see, what can we do here? Oh, we could oh, okay. I see something interesting. we can always like shift all of the weights down until x1 equals 1 because we particularly want the smallest, heaviest weight. And the inequalities here, like that I wrote on the screen, still hold if you just shift everything down by a constant. So we can actually assume that x1 is 1. And in fact, when x1 is 1, that's like the smallest it can be. So it'll eventually wind up giving us the smallest value of x8 possible as well. And this is nice too, because if x1 equals 1, we actually can like kind of figure out what x2 and x3 possibly can be. Because now x2 has to be greater than or equal to 2, and x3 has to be greater than or equal to 3. But this also makes like we have this using this inequality. Am I off screen? Let me move this a little bit. There we go. Using that the first inequality, the one right here, this one, we can sort of solve for what x4 can be. Because this is greater than x2 plus x3, which is greater than or equal to 5, which means taking this and this, we basically have x4 is greater than 4, which means x4 is greater than or equal to 5. And, oh, nice Fibonacci numbers pop up. That's interesting. That's fun. But basically using the same idea now, because we know that x3 is greater than or equal to 3, and x4 is greater than or equal to 5, we can use our second inequality here now to sort of solve for what x5 can possibly be. Or actually, we can just use x1. Wait, yeah, we can just use x1 again, because I guess using the small like the idea is if I have any like weights out of the 4 that's the heaviest, that like let's say xi is the heaviest out of 4 weights, xi plus x1, which is the smallest, should be greater than the other two. And if x1 is our weight that's paired up with the heaviest, if it's true for that pair, it's true for any other pair with x1 because that's the smallest possible pair along with xi. So what we're gonna do is sort of use the same logic but solve for x5 now. And I'm gonna assume it pops up being greater than or equal to 8, but we shall see. So I have x1 plus x5 is greater than is greater than x3 plus x4. And this is greater than or equal to 8. So yeah, x5 is greater than or greater than 7, which also means x5 is greater than or equal to 8. And you can crunch the numbers or notice the pattern, but basically repeating this process, you kind of just add up the least consecutive terms, and yeah, it's recursive. And you'll notice the numbers pop up being the Fibonacci because I don't know, you might want to try proving this after, but is it true that like out of any like 4, you could probably figure out some Fibonacci inequality with this, but you just basically end up getting that x5 is greater than or equal to 8, and then x6 should be greater than or equal to 13, x7 should be greater than or equal to 21, x8 should be greater than or equal to 34, and x9, oh yeah, x8 is our last one. So the minimum possible value of x8 is 34. I hope that's right. That was an interesting problem, actually. I enjoyed that one.
Yeah, that one was really fun. I liked it a lot as well, watching you solve that one. I see Matthew also says Fibonacci is related to phi, the golden ratio. Yeah, that's exactly right. And it's amazing that you remember this. Phi is a very special number. And also, it's a very special variable letter because the function phi of n is also very nice. Yeah. So feel free to investigate phi more. Yeah, but that was right. All right. Well, that was indeed the last question. And as you guys have astutely been noting, we are nearing the end of our time. So thank you all for joining us today. And if you like this, you can see more at live.poshenlo.com/math-kangaroo. And also you can feel free to contact support@poshenlo.com at any time or scan these QR codes. naturally, the one that says newsletter will lead you to the newsletter, and the one that says live.poshenlo.com/mathkangaroo will bring you to that website. I've always wondered how QR codes work. It's very weird. Yeah. Bye. Yeah.
Yeah, bye everyone. Thank you for coming.
Have a great week.
Oh, it's a unique binary pattern.
That's cool. Oh yeah, like binary as in this is a black square, this is a white
Yeah.
square.
But I
Yeah.
feel like there's gray squares, no? I feel like the squares have different colors.
Hmm.
Or maybe it doesn't matter.
No.
Maybe it's a colored square versus a not colored square.
Yeah, I don't think they're gray squares. At least I don't see any. Maybe I'm colorblind.
Oh, it's the blue coming in from your like the okay.
Oh, I
Yeah.
see.
Hmm. Actually, I will look into this. I wonder how QR codes work. I wonder how barcodes work for that matter, honestly.
Yeah. Maybe it's similar. Like all the barcodes seem to have a long number underneath them that they represent. So maybe
Oh,
the
do you think that's what it
barcode,
is?
yeah, like they're
That's
discrete
interesting.
slots, and
Yeah.
each slot is black or white for 1 or 0, and it's a number in binary.
Wait, but how many square? Oh, okay. What if
Yeah.
you run with squares?
Or like a slot for a really limited QR code system. And you could have bars here and like this. Or wait, maybe the length of the bars themselves, maybe the spacing between the bars is constant and the length of the bars vary. I do not remember. I
think
should look at a barcode. Oh,
I think the
okay.
thickness of the bars.
Yeah. So both the thickness of the bars and the spacing between the bars vary. So maybe a thicker bar is just many ones in a row.
Oh, probably. Yeah. Oh, but some are longer.
Huh, that's bizarre.
Oh, okay. No, I think those were just dividers, or perhaps. Oh,
Hmm. This is fascinating. Like the world is so fancy.
I'm curious now whether the number underneath the barcode represents like it's binary or something. That would be
Yeah.
interesting.
Oh, bye,
Are we-
Karsten.
I think we're disconnected, are we?
I'm not sure.
Let me
I
check.
think we maybe, or we might still be in the main room though. Ah, so there are apparently 95 different sections, and they're the lines that remain constant, the thin lines at the end and in the middle are guards. And hmm,
Yeah, that probably helps with scale. That's cool.
yeah,
Interesting
this is
conversation.
cool.
Did you write the problems or like help write the problems?
Oh, you're talking about me?
Yeah.
No, no, no. I usually just go over the problems like you do. But
Okay.
I don't know what's going on. That was some pretty nice.
Cool.
29 was interesting. I wonder how the person came up with the problem number 29.
Oh, yeah.
I have a professor who says that these sorts of problems, or at least competition problems, are sort of like a person finds something neat and says, "Oh, hey, that's cool. How do I make it less obvious that this is what I'm going for?" So maybe this
Yeah.
person noticed that Fibonacci numbers
I wonder what.
some
I wonder, yeah, I wonder what that thing was that he found. I bet like there's some inequality he saw, and then like 1 plus f of n plus 2 is greater than f of n plus 1 plus f of n. Is that true? Probably.
well, I don't immediately see any counterexample. Oh, wait a
It is
second.
true because that's the problem.
Yeah,
That is the
yeah.
problem. So it has to
And
be true.
also, yeah,
Yeah.
well, no, also if you had like some fx, it's the biggest one, and you have it doesn't matter what's going on here. You have the biggest numbers beneath it you can get are fx minus 1 and fx minus 2.
Oh,
But their sum
yes.
is exactly fx. So no matter
Oh,
what.
yeah. Okay, I see.
Yeah. So that's if you have the biggest, you win. If I don't know, if FA, I think it goes both ways.
Wait, but yeah, that automatically makes the thing true because the heaviest one is like bigger than the other ones at most plus
Yeah.
1. Yeah.
And that's why it was specifically 2 coins on each side, because that definitely does not hold for 3 coins. For example, 13, 2, no, wait,
Yeah.
21, 2, and 3 versus 13, 8, and 5.
You need that at least 1 because it could be equal to the other 2.
Wait,
Yeah.
I don't think it would work for 3, yeah. Maybe there's like a weird Fibonacci sequence with like 3 ones and then you add 3 at a time. It works out.
yeah, that one would.
That's cool.
If you had 3, wouldn't it be equal though, maybe?
Or
No, I
not
mean,
3
like,
of these, because like in this case you could get 34, 2 and 3, and then 21, 13, 8 overrides that. But I think what he was saying was the sequence 1, 1, 1, 3, 5, 9, 17.
Yeah, but
31.
like if you take 4 like of
Yeah.
them together, it's not going to be heavier. It'll be equal.
if you're doing 3 and 3, then
yeah.
you add 2. Yeah, maybe. That's weird. You have the heavy one and then. I mean, but still, you need the third one. You need 3 of the 3 ones before it. And so this one actually does
Yeah.
work.
Yeah. So in this case, it would be, I guess, fx, even if you have fx minus 1, fx minus 2, fx minus 3, they can be no bigger than fx,
Yeah.
which is okay. So maybe that's what they got it.
That's cool though.
That's probably
Yeah.
that makes sense. Okay. I think I'm gonna get off now. I have
Yeah.
Yeah. It was nice.
All right.
Yeah.
Yeah. If anyone's still
Bye.
watching this, thank you and goodbye.
Oh, I think we're off. From the
Okay. I
Okay.
hope. Yeah.
Makes sense.
Bye.
All right. See you guys.
Recording